Hello there and welcome to ThinkSleep. Tonight we're going to look beneath our feet and ask something that sits quietly at the edges of archaeology and history. What if those who came before us possessed advanced technologies we think belong only to our modern age? What if long before our Industrial Revolution, before our computers and machines, other civilizations discovered sophisticated capabilities that we're only now rediscovering? I don't mean mystical powers or visitors from elsewhere. I mean actual technical knowledge, emerging from human observation and ingenuity, following different pathways than our own, leaving traces so subtle we've learned to overlook them. Before we begin exploring these possibilities, I'd love to know where in the world you're listening from tonight. If this kind of quiet wondering appeals to you, I'd be grateful if you tapped like or subscribed. When we think about technological advancement, we usually picture it as a one-way journey from primitive to sophisticated, each age stacking neatly upon the last, one discovery building on top of another in an unbroken climb toward complexity. But what if this story is incomplete? What if knowledge doesn't only accumulate, but sometimes disappears? The Earth is incredibly old. 4.5 billion years of geological time, of continents drifting and mountains rising and falling. Human civilization occupies only the thinnest sliver of that vast timeline. And in such immense stretches of time, even the most durable evidence can be ground to dust, buried beneath miles of sediment, or swallowed by the slow churn of tectonic plates. What remains in the archaeological record might be only the faintest echo of what once existed. Consider what 10,000 years means in the life of a planet that's been turning for 4.5 billion years. If Earth's entire history were compressed into a single day, human civilization would occupy the final few seconds. And within those seconds, our industrial age would last less than a blink. This perspective isn't meant to diminish our achievements, but to help us understand how easily those achievements could vanish if given enough time. The weight of deep time presses down on everything. Mountains that seem eternal are ground to dust. Oceans that appear permanent shift their boundaries. Continents drift apart and crash together. The surface of the planet is constantly being recycled, renewed, erased. What we think of as solid ground is actually in constant motion, just too slow for us to perceive directly. When archaeologists dig into the past, they're working within this immense temporal framework. Every layer of Earth represents time compressed, stories pressed flat and stacked one atop another. But the deeper you go, the less detailed the story becomes. The archaeological record isn't a smooth continuum. It's full of gaps, discontinuities, missing chapters. Entire periods are represented by nothing more than a thin line of different-coloured sediment. This is why the idea of lost advanced technology is both fascinating and frustrating to explore. If such technology existed 50,000 years ago, or 100,000, the chances of finding clear evidence diminish dramatically. Not because it was primitive or crude, but because time itself becomes the enemy of preservation. Wood rots, metal corrodes. Stone structures can endure longer, but they too succumb to weathering, earthquakes, and the gradual reshaping of the landscape. Even our own technology, which we think of as so durable and permanent, would largely disappear given enough time. The plastic in our landfills might last for thousands of years, but that's still just a moment in geological terms. Our concrete foundations would crumble, our steel frameworks would rust away. In 100,000 years, most traces of our civilization would be gone, leaving only the faintest chemical signatures in the sediment. But deep time doesn't just erase physical objects, it erases memory, knowledge, entire ways of understanding the world. Languages disappear without a trace. Scientific insights are forgotten. Technical procedures that took generations to develop can be lost in a single catastrophe or social collapse. The libraries of Alexandria held the accumulated knowledge of the ancient Mediterranean world, and when they burned, countless texts vanished forever. Now imagine similar losses happening not once but repeatedly, across vast spans of time. This is perhaps the most profound way that deep time works against the preservation of advanced technology. It's not just that the machines break down or the buildings crumble, it's that the knowledge needed to understand and recreate those achievements gets lost. Even if we found the remains of some sophisticated ancient device, we might not recognize it for what it was. We might classify it as a natural formation, or a crude tool, or simply an anomaly not worth investigating. The weight of deep time also affects how we interpret what we do find. When archaeologists discover evidence of sophisticated ancient engineering, the natural assumption is that it represents the pinnacle of what was possible at that time. But what if it represents just a fragment, a single surviving example of capabilities that were once much more widespread? What if the anomalies we puzzle over are not exceptions, but the only survivors of entire technological traditions that have been otherwise completely erased? Consider the Antikythera mechanism, that remarkable ancient Greek device that can calculate astronomical positions and predict eclipses. For decades after its discovery, scholars struggled to understand what it was, because it seemed impossibly sophisticated for its time. It revealed that ancient Greeks had mechanical and mathematical knowledge far beyond what anyone had imagined. But here's the unsettling question. How many other such devices existed and were lost? How many other examples of ancient technological sophistication have been ground to dust by the weight of centuries? The ocean makes this problem even more acute. Sea levels have risen and fallen dramatically throughout human history. Vast areas that were once dry land are now underwater, and with them, any civilizations that might have existed there. The continental shelves where early human settlements would most likely have been located are now beneath hundreds of feet of water and sediment. It's entirely possible that entire chapters of human technological development are sitting on the ocean floor, inaccessible and invisible. When we look at the archaeological record, we're seeing only what has survived, not what once existed. It's like trying to understand a novel when 99% of the pages are missing. We piece together what we can from the fragments that remain, but we know the story is incomplete. The silences in the record might be just as significant as what we actually find. This doesn't mean we should abandon scientific rigor or accept wild speculation as fact, but it does mean we should hold our assumptions lightly. The absence of evidence is not evidence of absence, especially when dealing with timescales that can erase almost everything. When someone claims that ancient peoples couldn't have possessed advanced technology because we haven't found clear evidence of it, they're making an assumption about what deep time preserves and what it destroys. The weight of deep time is democratic in its erasure. It doesn't distinguish between the profound and the mundane, between the masterpiece and the mistake. It presses down equally on everything, turning civilizations into sediment, knowledge into silence, achievements into mysteries that we may never fully solve. When we hear the word technology, most of us immediately think of silicon chips and steel frameworks, of electricity flowing through copper wires and radio waves carrying information across vast distances. We imagine factories and laboratories, computers and smartphones, rockets and satellites. But this narrow definition might be one of the biggest obstacles to recognizing advanced technology from the past. What if intelligence took different paths, solved problems in ways we haven't considered, and left behind achievements that don't look anything like what we expect technology to be. Technology, at its most basic level, is simply applied knowledge. It's the human capacity to understand natural principles and harness them for practical purposes. A sharp stone deliberately shaped to cut is technology. So is a bow that uses stored energy to propel an arrow. So is the selective breeding of plants to increase their yield or nutritional value. So is the careful observation of star patterns to predict seasonal changes. These examples might seem primitive compared to our digital age, but they represent the same fundamental process: minds observing, understanding, and manipulating the world around them. The difference between what we call primitive technology and advanced technology isn't necessarily one of sophistication in thinking, but rather of accumulated knowledge and available materials. A hunter-gatherer who can track an animal across varied terrain, predict its behavior, and intercept it at exactly the right moment is demonstrating cognitive abilities that rival those of any modern engineer. The difference is in the cultural and technical foundation they're building upon. This suggests that ancient peoples with the same basic cognitive equipment we possess might have developed technological solutions that we simply don't recognize as technology because they don't match our expectations. Perhaps they mastered principles of physics, chemistry, or biology that we're only rediscovering now. Perhaps they found ways to work with natural processes rather than against them, creating systems so integrated with their environment that they appear natural to us. Consider the possibility of biological technology. While we're just beginning to explore genetic engineering and synthetic biology, ancient peoples might have developed sophisticated understanding of biological processes through careful observation and experimentation over thousands of years. They might have bred plants and animals not just for food, but for specific chemical compounds, structural properties, or even behavioral characteristics. They might have understood fermentation, enzyme processes, and other biochemical reactions in ways that allowed them to create materials and substances we don't associate with pre-industrial societies, or consider acoustic technology. We know that certain ancient sites have remarkable acoustic properties, allowing whispers to be heard clearly across great distances, or creating specific resonant frequencies in enclosed spaces. What if these weren't accidents of architecture, but deliberate applications of acoustic engineering principles? What if ancient builders understood how to manipulate sound waves for communication, for psychological effect, or even for practical applications we haven't yet imagined? There's also the possibility of what we might call soft technology, systems that don't require durable materials, but instead rely on organization, knowledge, and social structures. Ancient societies might have developed sophisticated information processing systems based on memory techniques, oral traditions, and social networks. They might have created computational systems using arrangements of stones, knots, or other simple materials that could perform complex calculations. They might have developed psychological and social technologies that allowed them to coordinate large-scale projects or maintain stability across generations. The Maya, for instance, developed mathematical concepts like zero and sophisticated astronomical calculations without metal tools or written alphabets as we understand them. Their achievements suggest that mathematical and scientific sophistication doesn't necessarily require the kinds of material technology we associate with advanced civilizations. They were working with different tools, but reaching comparable levels of understanding in certain domains. We also need to consider that ancient peoples might have developed along technological paths that we abandoned or never explored. While we focused on mechanical and electronic solutions, They might have mastered what we could call environmental technology, learning to work with natural forces and processes in ways that required minimal material intervention. They might have understood atmospheric dynamics, geothermal energy, or magnetic fields in ways that allowed them to accomplish things we do with complex machinery. Think about navigation technology. Polynesian navigators could cross thousands of miles of open ocean using knowledge of currents, wave patterns, star positions, and subtle environmental cues. They developed what amounts to a biological GPS system, using their own senses and accumulated cultural knowledge to accomplish feats of navigation that we now require satellites and computers to match. This represents a different kind of technological sophistication, one that integrates human capabilities with deep environmental knowledge rather than relying on external tools. The concept of advanced technology in the past becomes even more intriguing when we consider that truly sophisticated civilizations might have learned to work within natural limits rather than attempting to transcend them. While our technological development has focused on increasing power consumption and material throughput, ancient advanced civilizations might have focused on efficiency, sustainability, and integration with natural systems. Their most advanced technologies might have been designed to leave minimal traces, to work in harmony with environmental processes, and to be maintained across generations without depleting resources. This kind of technology would be almost invisible to archaeologists looking for the material signatures we associate with technological advancement. A civilization that mastered solar energy collection through biological systems, that developed transportation networks based on understanding natural flows and patterns, that created information storage systems integrated with landscape features, would leave behind traces that we might interpret as natural formations rather than technological achievements. When we expand our definition of technology to include all the ways that intelligence can be applied to solve problems and manipulate the environment, the possibilities become vast. Ancient peoples might have developed technologies based on principles we don't yet understand, using materials and processes we haven't yet explored, creating systems that functioned effectively but don't match our preconceptions about how technology should look or work. This doesn't mean we should accept any claim about ancient technology without evidence, but it does mean we should be cautious about dismissing possibilities simply because they don't fit our current technological paradigm. The absence of metal gears doesn't mean the absence of sophisticated mechanical understanding. The absence of electronic circuits doesn't mean the absence of complex information processing capabilities. And the absence of obvious material traces doesn't mean the absence of advanced applied knowledge. The Earth is not a museum. It doesn't preserve artifacts for future generations to admire. Instead, it's more like a vast recycling system, constantly breaking down and rebuilding, grinding materials into new forms, burying some things while exposing others. This creates what archaeologists call the preservation problem, and it's one of the most significant challenges in understanding what technologies might have existed in the distant past. Most materials that humans work with are temporary by geological standards. Organic materials like wood, leather, textiles, and paper decompose relatively quickly when exposed to moisture, oxygen, and biological activity. Even in ideal conditions, these materials rarely survive more than a few thousand years. Metal, which we think of as durable, corrodes over time, especially in the presence of water and acids. Bronze can last longer than iron in some environments, but even bronze artifacts show significant deterioration after centuries or millennia. The conditions required for long-term preservation are actually quite specific and rare. Extremely dry environments, like certain desert regions, can preserve organic materials for thousands of years. Waterlogged, oxygen-free environments, such as peat bogs, can also halt decay processes. Freezing conditions, like those found in glaciers or permafrost, can preserve materials almost indefinitely. But these conditions cover only tiny fractions of the Earth's surface, and most ancient civilizations didn't have the luxury of locating all their activities in preservation-friendly environments. Even when materials do survive in archaeological contexts, they often survive only partially, or in forms that make their original function unclear. A complex wooden mechanism might survive only as stains in the soil where the wood once lay. A sophisticated textile might leave behind only the metal threads that were woven into it. An advanced chemical process might be detectable only as unusual residues that could easily be misinterpreted as natural deposits. The preservation problem becomes exponentially worse as we go further back in time. While we have abundant artifacts from civilizations that existed a few thousand years ago, the material record becomes increasingly sparse as we push into deeper time. By the time we're looking at tens of thousands of years ago, we're often working with nothing more than scattered stone tools and occasional bone fragments. The absence of other materials doesn't necessarily mean they weren't being used. It might simply mean they haven't survived. Consider what would happen to our own technological civilization if it were subjected to the same preservational filters that affect ancient technologies. Our computers contain gold, silver, and other precious metals that might survive in recognizable form, but the silicon chips, plastic housings, and complex circuitry would largely disappear. Our buildings are constructed primarily of concrete, steel, and glass, materials that would deteriorate significantly over thousands of years, especially without maintenance. Even our most durable structures would eventually succumb to weathering, seismic activity, and vegetation growth. The digital nature of much of our information storage makes the preservation problem even more acute for modern technology. Magnetic storage media lose their data over time. Optical disks degrade when exposed to light and heat. Even our most permanent-seeming digital archives require constant maintenance and periodic migration to new storage systems to remain accessible. Without this ongoing human intervention, vast amounts of our recorded knowledge would become inaccessible within decades and completely lost within centuries. This suggests that truly advanced ancient technologies might have faced similar preservation challenges. If ancient peoples developed sophisticated information processing systems, they might have relied on materials and storage methods that were even less durable than our own. Biological systems, for instance, could theoretically be used for computation and information storage, but they would leave no traces once the organisms died. Acoustic or optical systems could perform complex functions without requiring durable materials at all. The preservation problem is also affected by the specific environmental conditions that prevailed in the past. Climate changes, sea level fluctuations, volcanic activity, and other natural processes have repeatedly altered the conditions under which ancient materials might have been preserved. Areas that were once dry and stable might now be underwater or subjected to tropical humidity. Regions that were once inhabited might now be buried under volcanic ash or glacial deposits. Even when materials do survive, they often survive in contexts that make them difficult to interpret. A sophisticated tool might be found far from where it was made or used, carried there by human migration, trade, or natural processes. A complex structure might be partially destroyed by later construction, earthquakes, or deliberate dismantling for building materials. Chemical processes in the soil can alter the composition of artifacts over time, making it difficult to determine their original properties or manufacturing methods. The preservation problem also affects how we sample the archaeological record. Excavations typically focus on areas where preservation is known to be good, or where surface artifacts suggest promising subsurface deposits. This creates a bias towards certain types of sites and certain types of materials. We might be systematically missing evidence from environments where preservation is poor, but where significant technological development occurred. Archaeological preservation is further complicated by the fact that the most advanced technologies are often also the most fragile. Precision instruments, delicate mechanisms, and sophisticated materials often require the most careful handling and specific environmental conditions to survive. The kinds of technologies that would most clearly demonstrate advanced capabilities in the past are precisely the kinds that would be least likely to survive to the present. There's also what we might call the recognition problem, which compounds the preservation problem. Even when unusual artifacts do survive, they might not be recognized as evidence of advanced technology if they don't match our expectations about what such technology should look like. An object that functioned as a sophisticated instrument might be classified as a decorative item or religious artifact if its technological purpose isn't obvious from its form. The preservation problem doesn't make it impossible to find evidence of advanced ancient technologies, but it does mean that such evidence would be rare, fragmentary, and easily overlooked. It suggests that we should be cautious about drawing negative conclusions from the absence of material evidence. The fact that we haven't found clear traces of ancient advanced technology doesn't necessarily mean it never existed. It might simply mean that the Earth has done what it always does, patiently recycling the works of intelligence back into the raw materials of possibility. Scattered across the world are stone structures that shouldn't exist, not because they defy the laws of physics, but because they seem to require capabilities that we don't associate with the peoples who supposedly built them. These megalithic monuments, with their precisely cut blocks and impossibly tight joints, challenge our assumptions about what ancient civilizations could accomplish with the tools we imagine they possessed. At Pumapunku, high in the Bolivian Altiplano, massive stone blocks lie scattered like the pieces of some giant's construction set. These aren't rough-hewn boulders, but precisely shaped architectural elements with complex interlocking surfaces, perfectly flat planes, and sharp angles that look almost machine-made. Some of the blocks weigh over 100 tons, yet they show evidence of having been cut, drilled, and shaped with an accuracy that would be challenging even with modern equipment. The precision is unsettling. Edges are straight within fractions of an inch across spans of many feet. Surfaces are so flat that you can barely slip a piece of paper between adjoining blocks. Drill holes are perfectly round and uniform in diameter. Complex three-dimensional cuts interlock with other pieces in ways that suggest the entire structure was designed as an integrated system, like a massive stone puzzle where every piece had its predetermined place. What makes these achievements particularly mysterious is their context. Pumapunku was built in a region where the hardest available tools were supposed to be bronze chisels and stone hammers. The blocks themselves are made of andesite and red sandstone, materials that are difficult to work even with steel tools. Yet someone somehow shaped these massive stones with a precision that rivals modern machining capabilities. Similar mysteries appear at other ancient sites around the world. The Great Pyramid of Giza displays construction tolerances that would be impressive even by contemporary standards. Its base is level to within just a few centimeters across its entire area. The sides rise at angles that vary by less than 1/100th of a degree from perfect. The internal passages are aligned with astronomical precision, pointing towards specific stars with an accuracy that suggests sophisticated surveying techniques. The blocks used in the pyramid's construction fit together so tightly that you can't insert a knife blade between them, despite weighing tons each. This level of precision requires not just skilled craftsmanship, but also advanced planning, precise measurement tools, and construction techniques that we don't fully understand. The conventional explanation involves ramps, levers, and enormous amounts of human labour. But the precision of the final result suggests capabilities that go beyond brute force and simple tools. At Sacsayhuaman near Cusco in Peru, massive stone blocks are fitted together in walls that have survived centuries of earthquakes that toppled later Spanish constructions built on top of them. Some of these blocks weigh hundreds of tons and have been shaped into complex polygonal forms that interlock perfectly with their neighbours. The joints are so tight that not even a thin blade can be inserted between them, yet each block has a unique shape that required individual cutting and fitting. The engineering challenges involved in creating these structures seem to exceed what we would expect from civilizations that supposedly lacked advanced mathematics, precision tools, and mechanical equipment. Moving blocks weighing hundreds of tons across difficult terrain, lifting them to precise positions, and shaping them to fit with tolerances measured in millimeters, all suggest capabilities that don't match our understanding of ancient technological limitations. But perhaps the most intriguing aspect of these megalithic structures isn't just their precision, but their apparent obsolescence. Many of these sites show evidence of multiple construction phases, with later builders using progressively cruder techniques. At many locations, you can see the difference between early construction, with its impossibly tight joints and precise shaping, and later additions that use smaller stones, rougher techniques, and mortar to fill gaps. This pattern suggests that the knowledge and capabilities required to create the most impressive megalithic structures were lost over time. Later generations, lacking the techniques of their predecessors, did their best to maintain and add to these monuments using the methods available to them, but they clearly couldn't match the precision and scale of the original construction. The tools allegedly used to create these structures add another layer to the mystery. Experiments with bronze and copper tools, wooden levers, and stone hammers have shown that it's theoretically possible to shape and move large stone blocks using these methods. But the time and labour requirements are enormous, and achieving the level of precision seen at sites like Pumapunku would require not just primitive tools, but also sophisticated measuring instruments, planning capabilities, and quality control systems. There's also the question of why these ancient builders chose to work with such massive blocks in the first place. From a purely practical standpoint, using smaller, more manageable stones would have been far more efficient. The decision to work with megalithic blocks suggests that the builders either had capabilities that made such work feasible, or that there were specific reasons why massive, precisely fitted stones were necessary for their purposes. Some researchers have suggested that these structures demonstrate knowledge of principles that we're only beginning to understand ourselves. The precision fitting might indicate understanding of thermal expansion and contraction, allowing the structures to move as a unit during temperature changes. The massive scale might reflect knowledge of seismic engineering, creating structures that can flex and move during earthquakes without losing their integrity. The acoustic properties of many megalithic sites also suggest sophisticated understanding of sound transmission and resonance. Chambers within some structures amplify voices or create specific acoustic effects that might have had practical or ceremonial purposes. The precise shaping and positioning of stones might have been designed to manipulate sound waves in ways that required advanced understanding of acoustic principles. What's particularly challenging about these anomalies in ancient architecture is that they exist in a context where we have no clear evidence of the advanced tools and techniques that would seem necessary to create them. It's as if we found a precision-machined engine in a medieval blacksmith's workshop. The object exists, but it doesn't fit with what we know about the capabilities of its supposed makers. This creates a dilemma for conventional archaeology. Either our understanding of ancient capabilities is incomplete, or these structures were created using methods that we haven't yet discovered or recognized. The precision and scale of megalithic architecture suggests that ancient builders possessed knowledge and techniques that were somehow lost or forgotten, leaving behind monuments that stand as silent testimony to capabilities that we're still trying to understand. The mystery deepens when we consider that many of these sites are found in locations that would have been extremely difficult to access and work in using primitive transportation methods. They're often built on mountain tops, in remote valleys, or in areas where quarrying and transporting massive stones would present enormous logistical challenges. Yet someone found ways to not only access these locations, but to execute construction projects there with a precision that continues to puzzle engineers today. In the corridors of museums around the world sit artifacts that whisper of metallurgical knowledge that shouldn't have existed when they were made. These objects, forged from alloys and worked with techniques that seem to predate their supposed invention by centuries or millennia, challenge our neat timeline of technological development. They suggest that ancient smiths and metalworkers possessed capabilities that we've only recently begun to understand ourselves. The Delhi iron pillar stands as perhaps the most famous example of this metallurgical mystery. Rising over 20 feet into the air in the courtyard of the Qutub complex in India, this iron column has stood exposed to the elements for more than 16 centuries without showing significant rust. The pillar's resistance to corrosion has puzzled metallurgists since they first began studying it systematically. The iron contains trace elements and has a microstructure that creates a protective layer, essentially making it self-maintaining in ways that weren't understood when it was supposedly forged around 400 CE. Modern analysis has revealed that the pillar's iron has an unusually high phosphorus content and low sulfur content, giving it properties that wouldn't be achieved in European iron working until much later periods. The forging technique required to create such a large uniform piece would have demanded not just skill, but also advanced understanding of temperature control, atmospheric conditions, and the behavior of iron at different stages of heating and cooling. The knowledge required to produce such an artifact suggests metallurgical sophistication that doesn't match our assumptions about ancient Indian technology. But the Delhi pillar isn't unique. Similar examples of advanced metallurgy appear in archaeological contexts around the world, often in circumstances that make their existence puzzling. In Peru, archaeologists have found evidence of platinum working by pre-Columbian peoples, despite the fact that platinum has a melting point of over 1,700 degrees Celsius, far higher than the temperatures achievable with the furnaces that these civilizations supposedly possessed. The La Tolita culture of ancient Ecuador created intricate ornaments from platinum and gold alloys, requiring not only the ability to reach extremely high temperatures, but also sophisticated understanding of how different metals behave when combined. Platinum is notoriously difficult to work, remaining solid at temperatures that would melt gold, silver, and copper. Working with platinum requires either extremely high temperature furnaces or powder metallurgy techniques that involve mixing platinum powder with other metals and fusing them through controlled heating. archaeological evidence suggests that ancient Ecuadorian metalworkers were using powder metallurgy techniques to create platinum-gold alloys thousands of years before these methods were developed in Europe. They somehow knew how to create the precise conditions needed to fuse platinum particles with gold, producing ornaments with complex shapes and fine detail that would be challenging even with modern equipment. Damascus steel represents another metallurgical mystery that has captured the imagination of researchers for centuries. The legendary blades forged in medieval Syria displayed properties that seemed almost magical. They could cut through European armour while remaining flexible enough to bend without breaking, and their surfaces showed distinctive watered patterns that were as beautiful as they were mysterious. The secret of Damascus steel was lost sometime around the 18th century, and despite extensive research, modern metallurgists have only recently begun to understand how these remarkable properties were achieved. The steel contained carbon nanotubes and carbide nanowires, microscopic structures that wouldn't be understood or deliberately created until the development of nanotechnology in the 20th century. The ancient smiths were somehow manipulating matter at the molecular level without understanding what they were doing in modern scientific terms. Recent analysis has shown that Damascus steel's unique properties came from the specific ore used in its production, wootz steel from India, combined with forging techniques that inadvertently created nanostructures within the metal. The smiths didn't understand the science behind what they were doing, but they had developed through trial and error the precise methods needed to produce these remarkable properties. This suggests that ancient metalworkers could achieve sophisticated results through empirical knowledge and careful observation, even without theoretical understanding of the underlying principles. The Lycurgus cup, a Roman artifact from the 4th century CE, demonstrates another form of advanced materials knowledge. The cup appears jade green when lit from the front, but glows ruby red when lit from behind, creating an almost supernatural effect. Modern analysis has revealed that the glass contains gold and silver nanoparticles dispersed throughout the material, creating what scientists now call a dichroic effect. The creation of such nanoparticles requires precise control of temperature, timing, and chemical composition during the glass-making process. The Roman craftsmen would have had to understand how to introduce metals into molten glass in exactly the right proportions and under exactly the right conditions to create particles measuring just 50 to 100 nanometers in diameter. This level of control suggests metallurgical and chemical knowledge that seems remarkably advanced for its time. Similar examples of sophisticated ancient metallurgy appear in cultures around the world. Chinese bronzes from thousands of years ago show evidence of advanced alloying techniques, producing metals with properties tailored for specific purposes. Some ancient Chinese mirrors were made from bronze alloys that remained bright and reflective for centuries, suggesting understanding of corrosion resistance that wasn't systematically studied in the West until much later. In South America, the Moshi civilization created ornaments using depletion gilding, a technique that involves removing copper from the surface of copper-gold alloys to leave a layer of pure gold. This process requires understanding of acids and chemical reactions that selectively dissolve one metal while leaving another intact. The technique produces objects that appear to be solid gold, but are actually sophisticated composite materials. The persistence of these metallurgical mysteries suggests that ancient peoples developed their expertise through centuries or millennia of experimentation and refinement. They might not have understood the atomic level processes involved, but they clearly developed empirical knowledge that allowed them to manipulate materials in sophisticated ways. This knowledge was probably passed down through closely guarded guild traditions, making it vulnerable to being lost during social upheavals or cultural disruptions. What makes these examples particularly intriguing is that they often represent isolated achievements that weren't built upon or developed further. The techniques for making Damascus steel were lost, and only recently partially recovered. The methods for creating dichroic glass apparently died with their Roman makers. The metallurgical knowledge that produced the Delhi iron pillar wasn't preserved in other similar artifacts. This pattern suggests that advanced metallurgical techniques existed in the past, but were fragile, dependent on specific knowledge traditions that could be broken by war, disease, or social collapse. The techniques themselves weren't primitive, but the systems for preserving and transmitting the knowledge were vulnerable in ways that made such achievements temporary and easily lost. The existence of these artifacts forces us to reconsider our assumptions about the linear development of technology. Perhaps metallurgical knowledge developed in waves, with periods of sophisticated understanding followed by periods of loss and rediscovery. Perhaps different cultures developed advanced techniques independently, achieving remarkable results through different approaches to the same fundamental challenges. In the quiet halls of museums and the dusty corners of private collections lie objects that seem to mock our understanding of what ancient peoples could accomplish with primitive tools. These artifacts display a level of precision, complexity, and technical sophistication that appears to exceed the capabilities of the technologies we believe were available to their makers. They sit like riddles carved in stone and metal, challenging us to explain how they came to exist. The crystal skulls that have fascinated researchers for over a century represent one category of these precision mysteries. Whether ancient or modern, the most carefully crafted examples display optical properties and surface finishes that would be difficult to achieve even with contemporary equipment. The Mitchell Hedges skull, perhaps the most famous, shows no tool marks under microscopic examination, suggesting it was shaped using techniques that left no trace of the working process. Creating such an object from a single piece of quartz crystal would require not only enormous patience and skill, but also understanding of crystal structure, optical properties, and the behavior of quartz under different types of mechanical stress. Quartz is nearly as hard as diamond and fractures unpredictably when worked incorrectly. Shaping it into complex three-dimensional forms with smooth surfaces and precise proportions would challenge even modern lapidary techniques. The Antikythera mechanism, discovered in an ancient Greek shipwreck, represents perhaps the most famous example of precision that seems to exceed its technological context. This bronze device, dating to around 100 BCE, contains gear trains with more than 30 meshing cogwheels, some with teeth so fine they're barely visible to the naked eye. The gearing ratios are calculated to track the movements of the sun, moon, and planets with remarkable accuracy. The precision required to create such gear teeth using ancient metalworking techniques is staggering. The teeth had to be cut with uniform spacing and precise angles to mesh properly with the joining gears. Any significant error in the cutting would have caused the mechanism to jam or produce inaccurate results. Modern attempts to recreate similar mechanisms using period-appropriate tools have proven extremely challenging, requiring exceptional skill and numerous failed attempts to achieve comparable precision. But the Antikythera mechanism isn't just precise in its construction, it's also mathematically sophisticated. The gear ratios encode complex astronomical calculations that require understanding of planetary motions, lunar cycles, and solar year variations. The device could predict eclipses decades in advance and track the 4-year cycles of Olympic Games. This suggests that ancient Greek craftsmen not only possessed remarkable mechanical skills, but also had access to astronomical knowledge that was previously thought to be much later developments. In the realm of stoneworking, ancient artifacts display precision that challenges our assumptions about what's possible with copper and bronze tools. The granite boxes found in the Serapeum of Saqqara in Egypt are carved from single blocks of granite, with internal dimensions that vary by less than a few thousandths of an inch. The corners are perfectly square, the surfaces are smooth to the touch, and the lids fit so precisely that the seam between lid and box is barely visible. Granite is one of the hardest stones commonly found in ancient construction, composed primarily of quartz, feldspar and mica. Working granite to such precision requires not only hard tools, but also sophisticated measuring instruments and quality control methods. The internal surfaces of these boxes are particularly puzzling, as they would have been extremely difficult to access and work using conventional hand tools, yet they show the same level of precision as the external surfaces. Similar precision appears in ancient Peruvian stonework, where craftsmen somehow created interlocking stone joints so tight that no mortar was needed, and so precise that the structures have survived centuries of earthquakes that toppled later Spanish buildings. Some of these joints involve complex three-dimensional curves that required each stone to be shaped to fit exactly with its neighbours. The precision of the fitting suggests not only skilled craftsmanship, but also sophisticated planning and measurement techniques. The Baghdad battery, a clay jar containing a copper cylinder and iron rod discovered in Iraq, represents another type of precision mystery. While its actual function remains debated, electrochemical experiments have shown that the device can produce small electrical currents when filled with acidic solutions. The construction shows understanding of galvanic principles and careful selection of materials to optimize electrical output. If the Baghdad battery was indeed designed to produce electricity, it demonstrates knowledge of electrochemistry that predates the supposed invention of the electric battery by more than 1,000 years. The precision lies not in mechanical construction, but in the selection and arrangement of materials to achieve specific electrochemical effects. Ancient optical devices present their own precision challenges. The Nimrud lens, a piece of ground crystal from ancient Assyria, has optical properties that suggest it was deliberately shaped to focus light. Creating such a lens requires understanding of refraction principles and the ability to grind curved surfaces with mathematical precision. The curvature must be uniform across the entire surface to avoid distortion, requiring techniques that weren't thought to exist in the ancient world. Some researchers have suggested that ancient peoples might have had access to precision tools that haven't survived in the archaeological record. Devices made from organic materials or constructed using techniques that left no permanent traces could have provided the capabilities needed to create these precise artifacts. Alternative theories suggest that ancient craftsmen developed empirical techniques that achieved precision through skill and experience rather than sophisticated instrumentation. The existence of these precision artifacts forces us to reconsider our assumptions about ancient technological capabilities. Either our understanding of ancient toolmaking is incomplete, or ancient peoples had access to methods and techniques that we haven't yet identified or understood. The precision exists in the artifacts themselves, regardless of how it was achieved. What makes these mysteries particularly intriguing is that they often represent isolated achievements that seem disconnected from the broader, technological context of their cultures. The Antikythera mechanism appears to be unique. No other similar devices have been found from the same period. The precision stonework of ancient Peru wasn't matched in other regions or time periods. These achievements seem to represent peaks of capability that weren't sustained or widely replicated. This pattern suggests that the knowledge and techniques required to create such precise artifacts might have been held by specialized groups or individuals, making them vulnerable to being lost during social disruptions or cultural changes. The precision that we marvel at today might represent the culmination of long traditions of refinement and experimentation that were then broken and forgotten. Scattered in archives and private collections around the world are maps that show things they shouldn't show. Coastlines that match geological features from thousands of years ago. Islands that existed only during ice ages. Continental outlines that correspond to landforms now buried beneath miles of ice or fathoms of ocean water. These cartographic anomalies suggest that someone, at some point in the distant past, possessed geographical knowledge that seems impossible given the supposed limitations of ancient exploration and surveying techniques. The Piri-Reis map of 1513 stands as perhaps the most discussed example of this cartographic mystery. Created by the Ottoman admiral and cartographer Piri-Reis, the map shows portions of the Atlantic Ocean, including the coasts of Europe, Africa, and South America. What makes the map remarkable isn't just its accuracy, but what it appears to show along the southern edge, a coastline that some researchers believe matches the northern coast of Antarctica as it would appear without its ice cap. The map predates the official discovery of Antarctica by more than 300 years, and the continent wasn't circumnavigated until the 1820s. Even more puzzling, if the southern coastline does indeed represent Antarctica, it shows features that correspond to the land beneath the ice sheet, information that wasn't available to modern cartographers until seismic surveys in the 1950s revealed the actual shape of the continent under its frozen covering. Piri-Reis himself noted on the map that he compiled it from earlier sources, some dating back centuries or even millennia. He mentions using charts captured from Spanish ships, as well as ancient maps that he doesn't identify more specifically. This suggests that the geographical knowledge displayed in his map might have been preserved and transmitted through multiple generations of cartographers, possibly tracing back to sources with access to information that seems impossible for their time period. The Orontius Phineus map of 1531 presents similar puzzles. This French cartographic work shows what appears to be a detailed representation of Antarctica, complete with mountain ranges, rivers, and coastal features. The continent is shown as ice-free and appears to be mapped with considerable detail and accuracy. Like the Piri-Reis map, this predates any known European contact with Antarctica by centuries. What makes these maps particularly intriguing is their apparent knowledge of geographical features that would only be visible or accessible under specific climatic conditions. If these maps do indeed show Antarctica, they would have required surveying during a period when the continent was not covered by ice. Geological evidence suggests that Antarctica was indeed ice-free or partially ice-free at various points in the distant past, but these periods predate known human civilization by thousands or tens of thousands of years. The Mercator map of 1569 adds another layer to this cartographic mystery. Gerard Mercator, one of the most skilled cartographers of his era, produced a world map that shows the Arctic region in remarkable detail, including what appears to be an accurate representation of Greenland's coastline and northern islands that weren't officially explored until much later periods. The map also shows a large Arctic landmass that some researchers believe corresponds to features that would only be visible if sea levels were significantly lower than they are today. These Arctic representations become particularly puzzling when we consider that much of the far north was supposed to be unexplored and unmapped during Mercator's lifetime. European exploration of the Arctic was limited and dangerous, with many expeditions ending in disaster. Yet Mercator's map shows these regions with a level of detail that suggests access to information gathered by systematic exploration and surveying. The Haji Ahmed map of 1559 presents yet another geographical anomaly. This Turkish map appears to show the Bering Strait as a land bridge connecting Asia and North America, along with detailed representations of Alaskan and Siberian coastlines that weren't officially mapped until centuries later. The land bridge corresponds to geographical conditions that existed during the last ice age, when lower sea levels exposed the seafloor between the continents. These maps raise profound questions about the sources of ancient geographical knowledge. If they are accurate representations of geographical features from thousands of years ago, they suggest that someone was conducting systematic exploration and mapping during periods when such activities supposedly didn't occur. The level of detail and accuracy would have required not only extensive travel and exploration, but also sophisticated surveying techniques and mathematical knowledge to translate three-dimensional geographical features into accurate two-dimensional representations. The creation of accurate maps requires more than just casual observation. Determining precise distances, angles, and proportions demands mathematical knowledge and measuring instruments. Creating maps that maintain accuracy across large areas requires understanding of spherical geometry and projection methods. The maps that show seemingly impossible geographical knowledge would have demanded sophisticated cartographic techniques that we don't associate with the periods when the underlying geographical information was supposedly gathered. There's also the question of how such geographical knowledge could have been preserved and transmitted across the long periods of time that would have been necessary. If these maps do show geographical features from Ice Age conditions, the information would have had to survive through thousands of years of cultural changes, migrations, and social upheavals. This suggests either remarkably stable traditions of geographical knowledge preservation or multiple independent discoveries of the same geographical information. The accuracy of some ancient maps in representing known geographical features adds credibility to their more mysterious aspects. The Piri Reis map, for instance, shows the coastlines of South America with remarkable precision, including details that weren't available to European cartographers of the early 16th century. This accuracy in known areas suggests that the mapmaker had access to reliable sources and sophisticated cartographic techniques. Some researchers have suggested that these anomalous maps might preserve knowledge from maritime civilizations that conducted extensive exploration during periods when geographical conditions were different from today. Rising and falling sea levels throughout geological history would have periodically exposed land bridges, islands, and coastal features that are now submerged. Civilizations with advanced navigation and exploration capabilities might have mapped these features during periods of accessibility. The navigational knowledge required to create such maps would have been considerable. Determining longitude, the east-west position, was notoriously difficult until the development of precise chronometers in the 18th century. Yet some of these ancient maps show accurate longitudinal relationships between distant geographical features, suggesting access to navigational techniques that we don't associate with early historical periods. The preservation of these maps through multiple copying and translation processes also suggests sophisticated systems for maintaining cartographic accuracy. Each time a map is copied, opportunities arise for errors, distortions, and misinterpretations. The fact that detailed geographical information appears to have been preserved through multiple generations of mapmakers suggests systematic approaches to maintaining accuracy that we might not expect from earlier periods. Across the ancient world, monuments and temples stand in precise relationship to the movements of celestial bodies, their stones arranged to capture solstices and equinoxes, to frame the rising of specific stars, to mark the subtle wandering of planets across the dome of night. These alignments reveal astronomical knowledge that seems to exceed what we would expect from peoples who supposedly lacked sophisticated instruments and mathematical systems. They suggest that ancient civilizations possessed understanding of cosmic cycles and celestial mechanics that rivals our modern knowledge in scope and precision. Stonehenge stands as perhaps the most famous example of ancient astronomical sophistication. The monument's primary axis aligns precisely with the sunrise on the summer solstice and sunset on the winter solstice, creating a calendar in stone that marks the turning points of the solar year. But the alignments go deeper than these obvious seasonal markers. The arrangement of stones also tracks the complex movements of the moon, including the 18-year cycle during which the moon's rising and setting positions shift to their extreme northern and southern points on the horizon. This lunar cycle, known as the Saros cycle, is subtle and requires careful observation over decades to detect and understand. The fact that Stonehenge's builders incorporated this knowledge into their monument suggests not only long-term astronomical observation, but also the mathematical capability to predict future lunar positions based on cyclical patterns. They were essentially creating an analog computer in stone, one capable of tracking and predicting celestial events with remarkable accuracy. The precision required to achieve these alignments is staggering when we consider the construction challenges involved. The monument's builders had to transport massive stones across hundreds of miles, position them with exact orientations, and create sightlines that would remain accurate despite the gradual settling and shifting that occurs in any large stone structure over centuries. This suggests not only astronomical knowledge, but also advanced surveying and engineering capabilities. Similar astronomical sophistication appears in monuments around the world. The temple complex at Angkor Wat in Cambodia is laid out as a terrestrial map of the cosmos, with its towers representing the peaks of Mount Meru, the center of the universe in Hindu and Buddhist cosmology. But beyond its symbolic meaning, the temple incorporates precise astronomical alignments that track the sun's movement through the year and align with specific constellations at astronomically significant times. The builders of Angkor Wat demonstrated understanding of the precession of the equinoxes, the slow wobble in Earth's axis that causes the positions of stars to shift gradually over thousands of years. This phenomenon wasn't officially recognized in Western astronomy until the work of Hipparchus in ancient Greece, yet it appears to have been incorporated into the design of Angkor Wat centuries earlier. The temple's orientation and proportions seem designed to maintain astronomical accuracy despite the gradual shifting of stellar positions over long periods. The pyramid complex at Giza displays astronomical knowledge that continues to puzzle researchers. The three main pyramids align with remarkable precision to the stars of Orion's belt as they appeared around 2500 BCE. But this alignment required understanding not just of the stars' current positions, but also of how those positions had changed due to precession and would continue to change in the future. The builders apparently calculated backwards to determine how Orion appeared at an earlier date, suggesting sophisticated mathematical astronomy. The Great Pyramid itself incorporates multiple astronomical alignments. Its passages point towards specific stars that held significance in ancient Egyptian religion and astronomy. The precision of these alignments is remarkable, with some passages aligned to celestial objects, with accuracy measured in fractions of degrees. Achieving such precision would have required surveying instruments and calculation methods that seem advanced for their supposed historical context. In the Americas, ancient astronomical knowledge reaches similar levels of sophistication. The Maya developed one of the most accurate calendar systems ever created, with calculations of the solar year that were more precise than those used in Europe until the Gregorian calendar reforms. Their astronomical tables could predict eclipses, planetary conjunctions, and the cycles of Venus with remarkable accuracy, often extending their predictions centuries into the future. The Maya astronomical codices reveal mathematical and observational capabilities that required not just casual sky-watching, but systematic recording and analysis of celestial phenomena over many generations. They tracked the synodic periods of planets, the intervals between successive oppositions or conjunctions, with precision that matches modern calculations. Their Venus tables, for instance, could predict the planet's appearances as morning and evening star across centuries with only minor accumulated errors. At Chichen Itza, the famous pyramid known as El Castillo demonstrates astronomical knowledge integrated into architectural design. During the spring and autumn equinoxes, the play of light and shadow on the pyramid steps creates the illusion of a serpent descending the structure. This effect required precise calculation of sun angles and careful positioning of architectural elements to create the desired visual result at exactly the right times of year. The Nazca lines in Peru represent another form of astronomical sophistication, with some of the massive ground drawings aligned to the rising and setting positions of important stars. The sheer scale of these alignments, some extending for miles across the desert, suggests not only astronomical knowledge, but also sophisticated surveying techniques capable of maintaining accurate orientations across vast distances. What makes these astronomical achievements particularly remarkable is the precision of the calculations involved. Predicting eclipses requires understanding of the complex orbital mechanics governing the relationships between Earth, Moon, and Sun. Tracking planetary motions demands knowledge of elliptical orbits and varying orbital speeds. Accounting for precession requires mathematical techniques capable of handling very small quantities accumulated over very long periods. The instruments supposedly available to ancient astronomers seem inadequate for the precision of their achievements. Simple sighting devices and basic angle measuring tools could provide rough orientations, but the accuracy displayed in many ancient astronomical alignments suggests access to more sophisticated measurement techniques. Some researchers have theorized about possible ancient instruments that haven't survived, perhaps made from organic materials or designed in ways that we don't recognize as scientific instruments. The mathematical knowledge required for these astronomical calculations also seems to exceed what we associate with ancient civilizations. Predicting celestial events requires understanding of trigonometry, spherical geometry, and methods for handling fractional quantities and accumulated errors over long periods. The Maya, for instance, used mathematical concepts including zero and place notation that weren't developed in Europe until much later. Perhaps most intriguing is the apparent integration of this astronomical knowledge into the broader cultural and religious systems of ancient civilizations. The alignments weren't just scientific curiosities, but were woven into the fabric of society, influencing architecture, agriculture, religious ceremonies, and social organization. This suggests that astronomical knowledge was both sophisticated and widely understood, at least among the educated classes, rather than being the specialized knowledge of a few individuals. The preservation and transmission of this astronomical knowledge across generations also represents a remarkable achievement. Maintaining accuracy in astronomical predictions requires continuous observation and periodic corrections to account for accumulated errors and gradual changes in celestial positions. Ancient civilizations apparently developed institutional systems capable of preserving and refining astronomical knowledge across centuries or millennia. In the dusty corners of archaeological sites around the world lie artifacts that hint at ancient understanding of forces we've only recently learned to harness. Strange objects that seem to respond to electrical current, architectural features that demonstrate acoustic properties beyond mere coincidence, and devices whose purpose remains mysterious but whose construction suggests knowledge of energy principles that supposedly weren't discovered until modern times. These enigmatic finds challenge our assumptions about when humans first began to understand and manipulate the invisible forces that surround us. The Baghdad battery, discovered in 1938 near Baghdad, consists of a clay jar containing a copper cylinder with an iron rod suspended inside. When filled with an acidic solution like vinegar or wine, the device produces a measurable electrical current of about 1 to 2 volts. The construction shows clear understanding of galvanic principles, the same basic concept that underlies all modern batteries. The copper and iron act as electrodes, while the acidic solution serves as an electrolyte, creating a simple but functional electrical cell. What makes this artifact particularly intriguing is its age. Dating to around 250 BCE to 250 CE, it predates Alessandro Volta's invention of the first modern battery by more than 1,500 years. If the ancient Mesopotamians who created this device understood its electrical properties, it suggests knowledge of electrochemistry that we don't associate with ancient civilizations. The question remains, what did they use it for? Experiments with replica Baghdad batteries have shown that they produce enough current to electroplate small objects, coating base metals with thin layers of gold or silver. This process, which we call electroplating, wasn't officially invented until the 19th century. Yet some ancient artifacts show evidence of metal coatings so thin and uniform that electroplating seems the most plausible explanation for how they were created. If ancient craftsmen were indeed using electrical current for decorative and practical purposes, it represents a technological capability that was somehow lost and not rediscovered for over a millennium. Similar electrical mysteries appear in other ancient contexts. Some researchers have noted that certain temple complexes in Egypt show evidence of unusual electrical properties. The Great Pyramid, for instance, can build up static electrical charges under specific atmospheric conditions. While this might be coincidental, some theorists have suggested that the pyramid's internal structure could function as a massive capacitor, storing and releasing electrical energy in ways that its builders might have understood and utilized. The acoustic properties of ancient structures present another category of energy mysteries. Many temple complexes and ceremonial sites around the world display sophisticated understanding of sound transmission, resonance, and echo effects that seem to go beyond what we would expect from accidental architectural choices. These buildings appear to have been deliberately designed to manipulate sound waves in specific ways. At Chichen Itza in Mexico, clapping your hands at the base of the main pyramid produces an echo that sounds remarkably like the call of the Quetzal bird, a creature sacred to the Maya. This acoustic effect required precise calculation of the pyramid's dimensions and angles to create the specific frequency response needed to transform a sharp clap into a bird-like chirp. The effect is so consistent and pronounced that it seems deliberate rather than coincidental. Similar acoustic engineering appears at sites throughout the ancient world. The theatre at Epidaurus in Greece can carry a whisper from the stage to the highest seats with perfect clarity, despite being built without modern understanding of acoustics or sound engineering. The design incorporates principles of wave reflection and interference that weren't systematically studied until centuries later. Some ancient chambers seem designed to create specific resonant frequencies that can induce altered states of consciousness in people inside them. The chambers beneath the pyramids at Giza, for instance, have been found to resonate at frequencies that correspond to human brainwave patterns. Whether this was intentional or coincidental remains debated, but the precision of the frequency matching suggests at least the possibility of deliberate acoustic engineering. The temples of Malta contain chambers with acoustic properties that amplify low-frequency sounds while dampening higher frequencies. This creates an environment where deep voices or drums would resonate powerfully while normal conversation would be muffled. Such selective acoustic filtering requires sophisticated understanding of sound wave behavior and careful architectural design to achieve specific acoustic effects. These acoustic anomalies raise questions about ancient understanding of sound as a form of energy that could be controlled and manipulated for practical or ceremonial purposes. Sound waves carry energy and can influence both physical objects and human psychology. If ancient builders understood these principles, they might have designed their structures to harness acoustic energy in ways we're only beginning to appreciate. The construction techniques required to achieve such precise acoustic effects also suggest advanced engineering capabilities. Creating specific resonant frequencies in large stone structures requires mathematical calculation of dimensions, careful selection of materials, and quality control during construction to ensure that the final result matches the intended design. Small errors in construction could completely destroy the desired acoustic effects. Some researchers have suggested that ancient temples might have functioned as more than just places of worship, possibly serving as centers for healing, meditation, or other practices that utilize specific acoustic or electromagnetic environments. The precise acoustic properties of these spaces might have been designed to facilitate altered states of consciousness, promote healing through sound therapy, or create psychological effects that enhanced religious experiences. The magnetic properties of certain ancient sites add another layer to these energy mysteries. Many megalithic sites around the world are located at points where the Earth's magnetic field shows unusual characteristics. Whether ancient peoples were aware of these magnetic anomalies and deliberately chose these locations, or whether the magnetic properties are coincidental, remains unclear. Some stone circles and ancient monuments appear to be constructed from rocks with unusual magnetic properties. The stones at some sites can deflect compass needles or produce measurable magnetic fields that don't correspond to the local geological conditions. If ancient builders were selecting stones based on their magnetic properties, it suggests awareness of magnetism as a natural force that could be detected and utilized. The precision with which some ancient sites are oriented to magnetic rather than true north also suggests possible understanding of the Earth's magnetic field. While magnetic north and true north don't coincide, ancient builders seem to have sometimes chosen magnetic alignments over astronomical ones, possibly indicating awareness of magnetic forces as distinct from celestial navigation references. These various examples of possible ancient energy knowledge don't prove that ancient civilizations possessed advanced understanding of electricity, magnetism, and acoustics comparable to modern physics, but they do suggest that ancient peoples might have developed empirical understanding of energy phenomena through careful observation and experimentation, even without the theoretical frameworks that guide our modern approach to these forces. The megaliths of the ancient world stand as silent monuments to engineering puzzles that continue to baffle researchers today. Massive stones, some weighing hundreds of tons, were somehow moved across vast distances, lifted to impossible heights, and positioned with precision that rivals modern construction techniques. The methods used to transport these enormous blocks remain largely mysterious, suggesting transportation technologies or techniques that we haven't yet identified or understood. At Baalbek in Lebanon, the Temple of Jupiter stands on a foundation platform built from some of the largest worked stones ever quarried. The trilithon, 3 massive blocks that form part of the temple's foundation, contain stones weighing an estimated 800 tons each. These blocks were quarried from a site over half a mile away, then transported across uneven terrain and lifted into precise position as part of a foundation that has remained stable for nearly 2,000 years. The logistics of moving such massive stones challenge our understanding of ancient capabilities. Modern heavy lifting equipment struggles with loads of this magnitude, requiring specialized cranes and transport vehicles that can distribute enormous weights across multiple axles and support points. The ancient builders of Baalbek somehow accomplished similar feats, using technologies that have left no clear traces in the archaeological record. Even more puzzling is the Stone of the Pregnant Woman, a massive limestone block that remains in the quarry at Baalbek, partially cut but never moved to the construction site. This stone weighs an estimated 1,000 tons and shows evidence of precise cutting and shaping work. The fact that it was abandoned suggests that the ancient builders had methods for quarrying and shaping such massive blocks, but that something prevented its transportation to the temple site. The quarrying techniques themselves represent another transportation mystery. Creating uniform blocks of such enormous size requires not only the ability to cut stone precisely, but also methods for moving and positioning the blocks during the quarrying process. The precision of the cuts and the uniformity of the blocks suggest sophisticated quarrying techniques that went far beyond simple hammering and chiseling. Easter Island presents transportation puzzles of a different but equally challenging nature. The famous Moai statues, some weighing 50 tons or more, were carved at quarries in the island's interior and somehow transported across miles of rough terrain to their final positions along the coastline. The island's isolation meant that the Polynesian inhabitants had to accomplish this feat, using only resources available on the island itself. Traditional explanations involve rolling the statues on logs or sliding them on wooden sledges, but experiments with these methods have proven problematic. The island had limited tree resources, making extensive use of logs for transportation questionable. The terrain between the quarries and the coast includes steep hills and rough ground that would make rolling or sliding massive stone figures extremely difficult. Recent experiments have suggested that the Moai might have been walked to their destinations, rocked back and forth using ropes attached to their heads, while teams of workers coordinated the movements to achieve forward motion. While this method has been demonstrated to work with replica statues, it requires remarkable skill and coordination, suggesting that the Easter Island inhabitants developed sophisticated techniques for moving heavy objects without wheels or large animals. The precision with which many ancient megalithic blocks were positioned adds another layer to the transportation mystery. At Sacsayhuaman in Peru, massive stones weighing hundreds of tons are fitted together with joints so tight that knife blades can't be inserted between them. Achieving such precision requires not only the ability to transport the blocks, but also methods for making fine adjustments to their positions during the construction process. The multi-angle cuts and complex interlocking shapes of many megalithic blocks suggest that positioning and alignment were accomplished with remarkable accuracy. Some blocks show evidence of having been lifted, repositioned, and adjusted multiple times during construction, indicating that the ancient builders had methods for handling massive weights with a level of control that seems to exceed what we would expect from primitive lifting techniques. The heights to which some megaliths were raised also present transportation challenges. At Pumapunku in Bolivia, massive stone blocks were lifted to positions high above the surrounding ground level. The site's elevation, over 12,000 feet above sea level, would have made any lifting operation more difficult due to the reduced oxygen availability that affects human physical performance at altitude. Some researchers have suggested that ancient builders might have developed techniques that we no longer understand or recognize. Theories range from sophisticated rope and pulley systems that left no archaeological traces to methods involving leverage and counterweights that could multiply human lifting capability beyond what we typically associate with ancient technology. The transportation of megaliths across water presents additional puzzles. Many massive stones were apparently moved across rivers, lakes, or even seas to reach their final destinations. The logistics of loading multi-ton blocks onto boats or rafts, transporting them across water without sinking the vessels, and then unloading them at the destination would have required sophisticated understanding of buoyancy, weight distribution, and marine engineering. At Stonehenge, the smaller blue stones were apparently transported from Wales, a distance of over 150 miles that would have required crossing multiple rivers and possibly sections of the Irish Sea. The exact route remains debated, but any path would have involved significant transportation challenges for stones weighing several tons each. The coordination required for these massive construction projects also suggests sophisticated organizational capabilities. Moving megaliths would have required not just physical techniques, but also planning, scheduling, and coordination of large teams of workers. The precision of the final results suggests that these projects were managed with remarkable efficiency and quality control. Some ancient transportation achievements seem to defy reasonable explanation using known techniques. The precision, scale, and difficulty of these accomplishments suggest that ancient peoples either possessed capabilities that we don't recognize, or that they developed techniques that were somehow lost without leaving clear traces in the historical record. The persistence of these transportation mysteries across different cultures and time periods suggests that the challenges weren't unique to any single civilization. Peoples around the world, working independently and often separated by thousands of years, somehow developed methods for moving massive stones that continue to puzzle modern engineers and archaeologists. In the shadowed archives of medical history lie accounts of surgical procedures, pharmaceutical knowledge, and anatomical understanding that seem to exceed the capabilities we associate with ancient healing traditions. These medical mysteries suggest that ancient physicians and healers possess sophisticated knowledge of human biology, chemistry, and surgical techniques that rivals modern medical understanding in certain specialized areas. The surgical instruments discovered in ancient Roman sites display a level of sophistication that matches many modern medical tools. Bronze and iron scalpels, forceps, surgical probes, and bone saws found in archaeological contexts show design principles that remain essentially unchanged in contemporary surgery. Some Roman surgical kits contain over 150 different specialized instruments, suggesting medical practices that involved complex procedures requiring precision tools designed for specific anatomical interventions. The quality of metallurgy in these ancient surgical instruments is particularly noteworthy. Many show evidence of careful heat treatment and alloying that produce steel-like properties in iron tools, creating sharp, durable cutting edges that could maintain their effectiveness through multiple uses. The precision of manufacture suggests understanding of both metallurgical principles and anatomical requirements that guided the design of each specialized instrument. Ancient medical texts describe surgical procedures that demonstrate remarkable anatomical knowledge. The Edwin Smith Papyrus, dating to around 1600 BCE, contains descriptions of brain surgery techniques that show understanding of cranial anatomy, neurological function, and surgical approaches that wouldn't be systematically studied again until much later periods. The text describes procedures for treating skull fractures, brain injuries, and spinal cord trauma with a level of detail that suggests extensive practical experience. Trepanation, the practice of drilling holes in the skull, appears in archaeological contexts around the world and across many time periods. While the purposes of these procedures remain debated, many trepanned skulls show evidence of healing, indicating that patients survived these operations and lived for months or years afterward. Achieving such survival rates for brain surgery using ancient techniques would have required sophisticated understanding of anatomy, infection control, and post-operative care. The precision of some ancient trepanation procedures is remarkable. Circular holes were cut through the skull bone with smooth, uniform edges that suggest the use of specialized tools and techniques. Some skulls show evidence of multiple trepanation procedures, indicating that these weren't desperate last resort interventions, but rather systematic medical treatments that were considered repeatable and survivable. Ancient pharmaceutical knowledge presents another category of medical mysteries. Many traditional medicines contain active compounds that weren't identified and understood scientifically until modern chemical analysis. Willow bark, used by ancient peoples for pain relief, contains salicylates that form the basis of modern aspirin. Foxglove, used traditionally for heart conditions, contains digitalis compounds that are still used in cardiac medications today. The precision with which ancient healers used these plant medicines suggests sophisticated understanding of dosage, preparation methods, and drug interactions. Many traditional remedies involve complex preparations that combine multiple plants in specific ratios, require particular extraction methods, or depend on timing of harvest and processing that affects the concentration of active compounds. Some ancient pharmaceutical preparations involved chemical processes that seem remarkably advanced for their supposed historical context. Egyptian embalmers used complex chemical mixtures that preserved organic tissues for thousands of years, demonstrating understanding of chemistry, bacteriology, and tissue preservation that required extensive experimentation and refinement. The effectiveness of mummification techniques suggests knowledge of biological processes and chemical interventions that went far beyond simple trial and error. Ancient Chinese medicine developed acupuncture systems based on understanding of anatomy and physiology that modern research has shown to correspond in many cases to actual nerve pathways, blood vessels, and anatomical structures. The precision with which acupuncture points are mapped and the consistency of these mappings across different ancient texts suggests systematic anatomical study and documentation. The manufacture of ancient medical instruments and pharmaceutical preparations also required understanding of chemistry, metallurgy, and quality control that seem sophisticated for early historical periods. Creating consistent, reliable medical tools and medicines would have demanded not just empirical knowledge, but also systematic approaches to testing, refining, and standardizing medical technologies. Archaeological evidence suggests that some ancient medical practices achieved results that seem impressive even by modern standards. Analysis of ancient skeletal remains shows evidence of successful bone setting, joint surgery, and even prosthetic devices that allowed patients to maintain mobility after traumatic injuries. Some ancient prosthetics show signs of wear that indicate years of functional use, suggesting that they were designed and fitted with remarkable precision. The preservation and transmission of medical knowledge across ancient civilizations also represents a sophisticated achievement. Medical texts from different cultures show evidence of shared knowledge and techniques that suggest communication networks and educational systems capable of maintaining and spreading complex information across vast distances and time periods. Cataract surgery appears in ancient Indian medical texts, with descriptions of techniques that closely parallel modern surgical approaches. The procedures described involve careful manipulation of the eye's internal structures using specialized instruments, suggesting understanding of ocular anatomy that required direct observation and systematic study of eye diseases and treatments. Some ancient medical achievements seem to represent isolated peaks of knowledge that weren't sustained or developed further. Advanced surgical techniques described in early texts sometimes disappear from later medical traditions, suggesting that the knowledge required to perform these procedures was lost during social disruptions or cultural changes. The integration of medical knowledge with other ancient sciences also suggests sophisticated understanding of the relationships between human health and environmental factors. Ancient physicians apparently understood connections between diet, climate, seasonal changes, and disease patterns that required systematic observation and record-keeping across multiple generations. In the ruins of ancient libraries and the fragments of text that survived the ravages of time, we glimpse what might have been vast repositories of knowledge that dwarf our modern understanding of information storage and preservation. These scattered remnants suggest that ancient civilizations developed sophisticated systems for recording, organizing, and transmitting complex information across generations, using methods that were both more durable and more vulnerable than our digital age technologies. The Library of Alexandria stands as the most famous example of ancient information storage, but what survives in historical accounts suggests it was far more than a simple collection of scrolls. Ancient descriptions indicate it functioned as a comprehensive information system that included not only written texts, but also maps, astronomical instruments, mathematical tools, and specimens of natural phenomena. The library apparently employed systematic methods for cataloguing and cross-referencing information that allowed scholars to locate specific knowledge within a collection that may have contained hundreds of thousands of individual items. The loss of Alexandria represents one of history's most profound information disasters. Modern estimates suggest that the destruction of the library eliminated more written knowledge than existed in all of Europe during the early medieval period. The texts that disappeared included works on mathematics, astronomy, medicine, engineering, and natural philosophy that weren't preserved elsewhere. Some ancient references describe scientific and technical knowledge that wouldn't be redeveloped until centuries or millennia later. But Alexandria wasn't unique. Similar information centers existed throughout the ancient world, many of which are known only through fragmentary references in surviving texts. The library at Pergamon reportedly rivaled Alexandria in scope and sophistication. The House of Wisdom in Baghdad served as a center for preserving and translating knowledge from multiple ancient traditions. These institutions suggest that advanced information storage and retrieval systems were more widespread than the surviving evidence would indicate. The methods used for preserving information in these ancient systems also appear to have been more sophisticated than simple writing on perishable materials. Some texts describe multi-layered encoding systems where information was preserved in multiple forms to ensure survival. Mathematical and astronomical knowledge, for instance, might be embedded in architectural proportions, encoded in mythological narratives and recorded in numerical tables, creating redundant storage systems that could preserve essential information even if individual components were lost. The Antikythera mechanism represents a form of information storage that encoded complex astronomical calculations in bronze gears and mechanical relationships. This device functioned as both a calculator and a database, capable of providing astronomical information across centuries of time. The precision of its calculations and the sophistication of its mechanical design suggest that similar devices might have existed for other types of technical knowledge. Ancient oral traditions also functioned as sophisticated information storage systems. The techniques used by traditional cultures to preserve complex information across generations involved elaborate memory systems that encoded knowledge in stories, songs, and ritual practices. These oral traditions often preserved technical and scientific information with remarkable accuracy across hundreds or thousands of years, suggesting that the distinction between written and oral information storage might be less significant than modern perspectives assume. The mathematical knowledge preserved in ancient texts reveals information storage systems that were capable of maintaining precision across multiple copying and translation processes. Mathematical papyri from ancient Egypt contain calculations and procedures that demonstrate understanding of complex algebraic and geometric principles. The consistency of these mathematical methods across different texts and time periods suggests systematic approaches to preserving and transmitting technical knowledge. Some ancient information storage systems appear to have been designed to survive catastrophic losses. The encoding of astronomical knowledge in temple architecture, for instance, created information storage that was physically durable and could be decoded by future generations even if the written records were destroyed. Similarly, the preservation of mathematical ratios in artistic and architectural works created multiple redundant copies of important numerical relationships. The translation networks that operated in the ancient world also represent sophisticated information management systems. The process of translating text between different languages and writing systems required not only linguistic skills, but also deep understanding of the technical content being preserved. The accuracy with which complex mathematical, astronomical, and medical knowledge was transmitted across linguistic boundaries suggests systematic approaches to maintaining information integrity during translation. Ancient libraries apparently employed classification systems that organized information according to sophisticated taxonomies. References in surviving texts describe methods for categorizing knowledge that took into account both subject matter and the relationships between different fields of study. These classification systems seem to have been designed to facilitate cross-referencing and the discovery of connections between different areas of knowledge. The physical design of ancient information storage facilities also suggests advanced understanding of preservation requirements. Some ancient libraries were constructed with features designed to control temperature and humidity, protect materials from light damage, and prevent access by insects and other destructive agents. These environmental controls required understanding of the factors that affect material preservation and the engineering capability to create stable storage environments. The loss patterns that affected ancient information storage reveal both the strengths and vulnerabilities of these systems. While some types of knowledge survived remarkably well across multiple civilizations and time periods, other categories of information disappeared almost completely. Technical knowledge related to manufacturing processes, for instance, seems to have been particularly vulnerable to loss, possibly because it was often preserved through apprenticeship systems that could be broken by social disruptions. The redundancy built into ancient information systems sometimes allowed knowledge to survive even when primary storage facilities were destroyed. Mathematical and astronomical knowledge, for instance, was often preserved in multiple forms across different cultures, allowing modern researchers to reconstruct ancient understanding even when original texts were lost. This suggests that ancient scholars understood the importance of distributed information storage and developed networks for sharing and preserving critical knowledge. The Earth has been resetting itself for billions of years, erasing civilizations not through malice, but through the simple mechanics of geological and climatological change. Ice ages advance and retreat, sea levels rise and fall, volcanic super-eruptions blanket continents in ash, and asteroid impacts periodically sterilize vast regions of the planet. These catastrophic events, recurring on cycles measured in thousands or millions of years, could explain why advanced ancient technologies seem to appear and disappear without clear continuity. The Younger Dryas period, which began around 12,900 years ago, represents one of the most dramatic climate reversals in recent geological history. In the span of just a few decades, global temperatures plummeted, ice sheets advanced rapidly across northern continents, and sea levels dropped dramatically. This climate catastrophe coincided roughly with the end of the Pleistocene megafauna extinctions, and may have contributed to major cultural disruptions among early human populations. The speed of this climate change is particularly striking from the perspective of technological preservation. A civilization that had developed sophisticated capabilities during the preceding warmer period would have faced not gradual decline, but sudden environmental collapse that left little time for orderly preservation of knowledge or technology. Coastal settlements would have been abandoned as advancing ice sheets made previously habitable regions uninhabitable. Trade networks that supported complex technologies would have been severed as populations migrated or died off. Archaeological evidence from this period shows clear signs of cultural disruption. The Clovis culture in North America, which had developed sophisticated stone tool technologies, appears to have vanished abruptly around the time of the Younger Dryas onset. While some of their technological innovations persisted in later cultures, the specific methods and organizational systems that supported Clovis technology were apparently lost and never fully recovered. The Toba supervolcanic eruption, which occurred approximately 74,000 years ago, provides an even more dramatic example of how catastrophic events can reset human development. This eruption in present-day Indonesia ejected so much ash and sulfur compounds into the atmosphere that it triggered a global volcanic winter lasting several years. Genetic evidence suggests that human populations were reduced to perhaps a few thousand individuals worldwide, creating a population bottleneck that could have eliminated entire technological traditions. The scale of the Toba eruption is difficult to comprehend. The volcanic winter would have reduced global temperatures by several degrees, shortened growing seasons, and made large regions temporarily uninhabitable. Any technological knowledge that wasn't preserved by the small surviving populations would have been lost permanently. Even if sophisticated technologies had existed before Toba, the survivors would have faced immediate survival challenges that made preserving complex knowledge systems a lower priority than basic subsistence. Ocean level fluctuations throughout geological history have repeatedly submerged and exposed vast areas of continental shelf that would have been prime locations for early civilizations. During ice ages, sea levels dropped by more than 300 feet, exposing land bridges and coastal plains that are now under hundreds of feet of water. When the ice melted, these areas were flooded rapidly, often within centuries rather than millennia. The Doggerland region between Britain and continental Europe represents a dramatic example of how sea level changes can eliminate entire inhabited regions. This area, which was above sea level during the last ice age, supported forests, rivers, and human settlements. When post-glacial flooding submerged Doggerland around 8,000 years ago, any evidence of human occupation was buried under North Sea sediments, where it remains largely inaccessible to archaeological investigation. Similar submergence events occurred around the world as glacial ice melted and sea levels rose. The Persian Gulf, much of which was dry land during Ice Age periods, was flooded relatively rapidly as sea levels rose. The continental shelves around Australia, Southeast Asia, and the Americas all experienced massive inundation that buried any coastal settlements under water and marine sediments. These flooding events would have been particularly devastating for technological preservation because coastal regions are typically where the most advanced settlements develop. Access to marine resources, trade routes, and river transportation makes coastlines attractive for population centres and technological development. The submergence of these areas would have eliminated precisely the locations where we would be most likely to find evidence of advanced ancient technologies. Asteroid and comet impacts provide another mechanism for catastrophic reset events that could eliminate technological civilizations. The Chicxulub impact that ended the age of dinosaurs 66 million years ago demonstrates the planet-wide effects that large impacts can produce. While such massive impacts are rare, smaller events that could still cause regional or global disruption occur more frequently on geological timescales. The Tunguska event of 1908, which flattened forests across thousands of square kilometers in Siberia, was caused by a relatively small cosmic object. A similar impact over a populated region could eliminate entire civilizations while leaving minimal evidence of the cause. The randomness of impact events means that even highly advanced civilizations could be destroyed without warning, regardless of their technological capabilities. Volcanic eruptions on scales larger than anything recorded in human history have occurred repeatedly throughout geological time. The Yellowstone caldera has produced super eruptions that covered much of North America in ash layers several feet thick. The Taupo eruption in New Zealand ejected enough material to significantly affect global climate. These events occur roughly every few 100,000 years, making them relatively frequent on the timescale of human evolution. Such eruptions would not only cause immediate destruction in affected regions, but would also trigger global climate effects lasting years or decades. The ash and sulfur compounds ejected into the atmosphere would reduce solar radiation reaching the Earth's surface, causing global cooling and agricultural failures. Civilizations dependent on complex agricultural systems would face collapse even if they were geographically distant from the eruption site. The periodicity of these catastrophic events suggests that Earth's climate and geology operate on cycles that could repeatedly interrupt technological development. Ice ages occur roughly every 100,000 years. Major volcanic eruptions happen every few 100,000 years, and significant asteroid impacts occur on million-year timescales. These overlapping cycles of disruption could explain why technological development appears to restart repeatedly, rather than showing smooth linear progress. The recovery time from major catastrophic events also affects technological preservation. Even if some knowledge survived an initial catastrophe, the social and economic disruption could prevent its systematic preservation and transmission. Survivors of major disasters typically focus on immediate subsistence needs, rather than maintaining complex technological systems that might not provide immediate survival benefits. In the quiet laboratories where geneticists study ancient DNA and the field stations, where botanists examine wild plant varieties, mysteries emerge that suggest our ancestors might have possessed biological knowledge far exceeding what we typically associate with pre-scientific civilizations. These biological anomalies hint at sophisticated understanding of genetics, selective breeding, and biological manipulation that seems to anticipate modern biotechnology by thousands of years. The domestication of corn from its wild ancestor, teosinte, represents one of the most dramatic examples of ancient genetic manipulation. Wild teosinte bears little resemblance to modern corn, producing only a few small seeds encased in hard shells that would be nearly impossible to harvest efficiently. The transformation from teosinte to corn required selective breeding that altered fundamental aspects of the plant's genetics, changing seed size, kernel attachment, plant architecture, and reproductive strategy. What makes this achievement remarkable is the sophistication of genetic changes involved. Modern analysis shows that the domestication of corn required coordinated modifications to multiple genes, affecting different aspects of plant development. Some of these changes would have had negative effects on plant survival in wild conditions, meaning that early agriculturalists had to maintain artificial growing conditions while selecting for traits that made the plants more dependent on human intervention. The speed with which this transformation occurred also suggests systematic breeding programs rather than gradual accidental selection. Archaeological evidence indicates that the major changes from teosinte to early corn varieties occurred within a few thousand years, a relatively short period for such dramatic genetic modifications. This timeline suggests that ancient plant breeders understood principles of heredity and selection that allowed them to guide genetic changes in specific directions. Similar sophisticated plant breeding appears in other ancient agricultural systems. The development of wheat from its wild ancestors involved coordinated changes to multiple characteristics including seed size, plant height, maturation timing, and seed retention. These modifications required understanding of how different traits were inherited and how selective breeding could be used to combine desirable characteristics from different parent plants. The ancient development of polyploid crops adds another layer of genetic sophistication. Many domesticated plants, including wheat, oats, and strawberries, have multiple complete sets of chromosomes that make them genetically more complex than their wild ancestors. The creation of polyploid varieties requires specific breeding techniques and often involves hybridization between different species, followed by chromosome doubling that can occur naturally but is rare enough to require systematic breeding programs to capture and maintain. Ancient animal breeding also demonstrates sophisticated understanding of inheritance patterns and genetic manipulation. The development of domestic dog breeds from wolves involved not only behavioral selection, but also dramatic changes to physical characteristics, growth patterns, and reproductive cycles. The diversity of dog breeds that existed in ancient times suggests systematic breeding programs that could selectively enhance or suppress different traits. The creation of specific horse breeds in ancient cultures required understanding of how physical and behavioral characteristics were inherited. Ancient horse breeders developed animals specialized for warfare, transportation, agriculture, and ceremonial purposes, indicating ability to selectively breed for complex combinations of traits, including size, speed, temperament, and endurance. Some ancient breeding achievements seem to exceed what we might expect from trial-and-error selection methods. The development of silk-producing silkworms, for instance, required not only understanding of insect biology and life cycles, but also methods for maintaining and breeding insects that were completely dependent on human care. The silkworms became so specialized through selective breeding that they could no longer survive in wild conditions. Ancient medical practices also suggest sophisticated understanding of biological processes that seems advanced for their historical context. Traditional medicines often involved complex preparations that required understanding of plant chemistry, extraction methods, and biological effects that went beyond simple empirical observation. The use of biological pest control in ancient agricultural systems demonstrates ecological knowledge that anticipates modern integrated pest management approaches. Some ancient cultures developed methods for encouraging beneficial insects and birds that controlled crop pests, suggesting understanding of ecological relationships and biological control mechanisms. Fermentation technologies developed by ancient cultures involved sophisticated understanding of microbiology, even without knowledge of microorganisms themselves. The production of bread, beer, wine, cheese, and fermented vegetables required control of environmental conditions that selected for beneficial microorganisms while suppressing harmful ones. The consistency and quality of ancient fermented products suggests systematic understanding of the biological processes involved. Some ancient biotechnologies involved manipulation of microorganisms for specific purposes. The production of certain dyes, pharmaceuticals, and industrial materials by ancient cultures required controlled fermentation processes that produced specific chemical compounds. These biotechnologies suggest understanding of how environmental conditions could be manipulated to guide biological processes toward desired outcomes. The preservation of seeds and maintenance of genetic diversity in ancient agricultural systems also demonstrates sophisticated biological knowledge. Many traditional cultures developed methods for storing seeds across multiple growing seasons and maintaining genetic diversity within crop populations. These practices required understanding of seed biology, genetics, and population management that prevented inbreeding depression and maintained adaptive potential. Ancient understanding of hybridization and grafting techniques enabled the development of fruit and nut varieties that combined characteristics from different parent plants. These techniques required knowledge of plant biology and compatibility relationships between different species and varieties. The success of ancient grafting programs suggests systematic experimentation with different combinations and techniques. The biological knowledge required for these achievements would have demanded not only empirical observation, but also systematic record-keeping, experimental approaches, and institutional systems for preserving and transmitting technical knowledge across generations. The sophistication of ancient biological manipulation suggests that early civilizations developed scientific approaches to understanding and controlling biological processes that were more advanced than typically assumed. Beneath the waves that have risen and fallen countless times throughout Earth's history lie the ruins of civilizations we may never discover. The ocean floor holds secrets that make archaeological investigation on land seem simple by comparison, concealing evidence of human achievement beneath miles of water and centuries of sediment accumulation. If advanced technologies existed in coastal regions during periods of lower sea level, most of that evidence now rests in locations that are virtually inaccessible to systematic study. During the last ice age, sea level stood more than 400 feet lower than today, exposing vast continental shelf areas that are now completely submerged. These exposed shelves would have provided ideal conditions for human settlement. Access to both marine and terrestrial resources, river mouths with fresh water, natural harbours protected from ocean storms, and relatively flat terrain suitable for construction. The areas we would most expect to find evidence of advanced ancient civilizations are precisely the areas now buried under hundreds of feet of seawater. The Doggerland region between Britain and continental Europe exemplifies how dramatically post-glacial flooding changed the world's geography. This area, roughly the size of England, supported forests, rivers, and human populations during the Ice Age. When rising seas submerged Doggerland between 8,000 and 6,000 years ago, any evidence of human occupation was buried under North Sea sediments, where it remains largely beyond the reach of archaeological investigation. Fishing trawlers occasionally bring up artifacts from the North Sea floor, including stone tools, animal bones, and fragments of worked wood that hint at the human presence that once existed in this now submerged landscape. But these chance discoveries represent only the tiniest fraction of what might exist beneath the seafloor sediments. The systematic investigation that would be needed to understand the scope and sophistication of Doggerland settlements remains technically and economically prohibitive. Similar submergence events occurred around the world as glacial ice melted and sea levels rose. The Persian Gulf, much of which was dry land during Ice Age periods, contained river valleys and coastal plains that could have supported substantial human populations. The flooding of this region was rapid in geological terms, occurring over just a few thousand years as meltwater from retreating ice sheets caused global sea levels to rise. The continental shelves around Australia contain submerged river systems and coastal features that indicate extensive land areas were above sea level when early humans first arrived in the region. The advanced seafaring capabilities required to reach Australia suggest that these early populations might have developed sophisticated maritime technologies, but any evidence of coastal settlements from this period now lies beneath the waters surrounding the continent. Off the coasts of India and Southeast Asia, vast shelf areas were exposed during low sea level periods, creating land connections between regions that are now separated by deep water. The Sunda Shelf, which connected mainland Southeast Asia with Indonesia and Malaysia, contained river systems and coastal plains that could have supported large populations and complex societies. The submergence of these areas would have eliminated evidence of any technological developments that occurred in these prime settlement locations. The technical challenges of underwater archaeology make systematic investigation of these submerged landscapes extremely difficult. Even in relatively shallow areas, excavation beneath the seafloor requires specialized equipment and techniques that are expensive and time-consuming. The deeper and more remote the target area, the more technically challenging and costly the investigation becomes. Most underwater archaeological work has focused on shipwrecks and sites in relatively shallow, accessible waters. The investigation of submerged landscapes requires different approaches and capabilities, including the ability to locate and identify subtle features buried beneath seafloor sediments. Side-scan sonar and sub-bottom profiling can detect anomalous features beneath the seafloor, but distinguishing between natural geological formations and human-made structures requires extensive ground truthing with cores and excavations. The preservation conditions in marine environments also create both opportunities and challenges for archaeological investigation. Waterlogged, anaerobic conditions can preserve organic materials that would quickly decay in terrestrial environments, potentially preserving evidence of ancient technologies that used wood, leather, and other perishable materials. However, the same conditions that preserve organic materials can also destroy metals and stone through chemical and biological processes. The sediment accumulation rates in marine environments mean that even relatively recent human activities can be buried beneath substantial deposits. In areas with high sedimentation rates, settlements from just a few thousand years ago might be buried under dozens of feet of sediment, making their detection and investigation extremely challenging. The few underwater archaeological sites that have been systematically investigated reveal the potential for remarkable preservation of ancient settlements. The submerged Neolithic village at Atlit Yam off the coast of Israel contains stone structures, hearths, and organic remains that provide detailed insights into ancient coastal life. The site was abandoned around 9,000 years ago, possibly due to rising sea levels, and was preserved beneath marine sediments until its discovery by underwater archaeologists. Similar submerged sites have been discovered in other parts of the world, but these represent only a tiny fraction of what might exist on the world's continental shelves. The technical requirements and costs associated with underwater investigation mean that most submerged archaeological sites remain undiscovered and uninvestigated. The implications of this preservation bias are significant for understanding ancient technological development. If the most advanced ancient civilizations developed in coastal regions that are now submerged, our understanding of ancient capabilities would be systematically biased toward less sophisticated settlements in inland areas that happen to remain above sea level. Hidden within the mythologies, religious texts and epic narratives of ancient cultures lie descriptions that some researchers believe contain encoded technical knowledge, compressed into symbolic language that preserved scientific and engineering principles across millennia. These ancient texts, when examined through the lens of modern technology, reveal descriptions that seem remarkably similar to advanced technical processes, suggesting that complex knowledge might have been deliberately encoded in religious and mythological frameworks to ensure its survival. The Vedic texts of ancient India contain descriptions of flying vehicles called vimanas that include detailed specifications for construction, operation, and navigation. These accounts describe craft capable of vertical takeoff, high-speed travel, and advanced navigation systems. While most scholars interpret these descriptions as mythological or symbolic, some researchers have noted that the technical details correspond remarkably closely to principles of aerodynamics and propulsion that weren't systematically understood until modern times. The Vaimanika Shastra, though its authenticity and antiquity remain debated, contains descriptions of aircraft construction that include specifications for metals, fuel systems, and operational procedures. Some of the metallurgical processes described in the text correspond to advanced alloying techniques that produce materials with properties similar to modern aerospace alloys. Whether these descriptions represent ancient technical knowledge or later interpolations remains controversial, but the level of technical detail suggests familiarity with engineering principles. Similar technical descriptions appear in other ancient traditions. The Book of Ezekiel contains detailed descriptions of a vehicle or structure with wheels within wheels, multiple faces, and the ability to move in any direction without turning. Modern aerospace engineers examining these descriptions have noted similarities to gyroscopic navigation systems and multi-directional propulsion concepts. While traditionally interpreted as mystical visions, the technical precision of the descriptions suggests possible encoding of mechanical principles. The Epic of Gilgamesh and other Mesopotamian texts contain descriptions of weapons and technologies that seem to anticipate modern military capabilities. References to weapons that could destroy entire cities with fire and light, create storms and floods, and level mountains bear striking similarities to descriptions of nuclear weapons and other advanced military technologies. The technical details embedded in these narratives suggest knowledge of energy release mechanisms and environmental effects that correlate with modern understanding of nuclear physics. Ancient Hindu texts describe weapons called astras that exhibit characteristics resembling modern directed energy weapons, including the ability to track targets, penetrate defensive barriers, and cause specific types of destruction. The Mahabharata contains descriptions of weapons that produce effects similar to radiation poisoning, including hair loss, nail damage, and delayed death that matches symptoms of radiation exposure. These descriptions predate the discovery of radioactivity by thousands of years. The precision with which ancient texts describe technical processes suggests that the authors possessed detailed knowledge of the subjects they were encoding. The metallurgical processes described in various traditions include specific temperature requirements, timing sequences, and material combinations that produce results consistent with advanced engineering principles. The accuracy of these technical specifications implies empirical knowledge rather than purely imaginative speculation. Some ancient texts contain mathematical and astronomical knowledge embedded within narrative structures that preserve precise numerical relationships and calculation methods. The positioning of events within mythological chronologies often corresponds to accurate astronomical periods and cycles. The preservation of complex mathematical relationships within story frameworks suggests deliberate encoding techniques designed to maintain numerical accuracy across multiple generations of oral and written transmission. The chemical processes described in alchemical text from various traditions contain technical procedures that correspond to modern chemical reactions and material synthesis methods. While couched in symbolic language involving gods, mythological creatures, and spiritual transformations, many alchemical procedures describe accurate chemical processes for creating specific compounds, extracting metals from ores, and producing materials with desired properties. Ancient medical texts often contain diagnostic and treatment procedures embedded within religious or philosophical frameworks. The technical accuracy of anatomical descriptions and pharmaceutical preparations suggests systematic empirical knowledge that was encoded within traditional narrative structures to ensure its preservation. The effectiveness of many traditional medical practices validates the technical knowledge preserved within these texts. The astronomical knowledge preserved in mythological narratives often demonstrates sophisticated understanding of celestial mechanics, encoded within stories about gods and mythological events. The timing and characteristics of mythological events frequently correspond to astronomical phenomena with precision that requires systematic observation and mathematical calculation. These correlations suggest that complex astronomical knowledge was deliberately preserved within cultural narratives. The engineering principles described in various ancient texts include accurate descriptions of mechanical advantage, structural engineering, and materials science concepts. Temple construction manuals contain specifications for foundation design, load distribution, and structural stability that align with modern engineering principles. The technical accuracy of these specifications suggests empirical knowledge of structural mechanics and materials behavior. The preservation of technical knowledge within religious and mythological frameworks provided multiple advantages for knowledge transmission across generations. Religious texts were more likely to be carefully preserved and accurately copied than purely technical manuals. The integration of technical knowledge with cultural and spiritual values ensured that the information would be maintained as an essential part of cultural identity rather than being discarded during social changes. In the quiet laboratories and workshops of today, scientists and engineers occasionally stumble upon rediscoveries that humble our assumptions about technological progress. Ancient formulations for concrete that grow stronger with age, metallurgical techniques that produce properties we struggle to replicate, and manufacturing processes that achieve results through methods we're only beginning to understand. These modern rediscoveries suggest that technological development isn't always linear, and that ancient peoples sometimes achieved solutions that we abandoned or forgot, only to rediscover centuries or millennia later. Roman concrete represents perhaps the most famous example of ancient technology that exceeds modern capabilities in certain applications. While modern concrete typically deteriorates over decades or centuries, Roman concrete structures have grown stronger over 2,000 years of exposure to seawater and weather. The Pantheon in Rome, built nearly 2 millennia ago, still stands with its massive concrete dome intact, while many modern concrete structures require significant maintenance or replacement within decades of construction. Recent analysis of Roman concrete has revealed the secret to its durability: the use of volcanic ash from specific sources that creates chemical reactions within the concrete matrix. The volcanic ash contains compounds that continue to react with water and carbon dioxide over centuries, causing the concrete to self-heal small cracks and actually become more resilient over time. This self-strengthening property wasn't understood until modern materials scientists began studying Roman structures systematically. The Romans also developed concrete formulations that were specifically adapted to different environments and applications. Their underwater concrete used different mineral compositions that performed better in marine conditions than many modern formulations. Harbour structures built with Roman marine concrete have survived 2,000 years of tidal action and storms, while modern seawalls often require replacement within decades. Damascus steel represents another ancient technology whose secrets were lost and only partially recovered through modern materials science. The distinctive watered patterns and exceptional properties of Damascus blades resulted from the presence of carbon nanotubes and carbide nanowires within the steel matrix. These microscopic structures weren't identified until the development of electron microscopy in the 20th century, yet ancient smiths were somehow incorporating them into steel through their forging processes. Modern attempts to recreate Damascus steel have achieved mixed success. While metallurgists now understand the basic principles that created the steel's exceptional properties, replicating the exact conditions and materials used by ancient smiths remains challenging. The specific ores and forging techniques that produced the original Damascus steel created conditions that favoured the formation of nanostructures in ways that are difficult to control using modern industrial processes. The Chinese developed cast iron production techniques more than 2,000 years before similar capabilities appeared in Europe. Their blast furnace designs achieved temperatures and controlled atmospheric conditions that produced high-quality iron with properties that matched or exceeded later European developments. The Chinese also developed steel production methods, including crucible steel techniques, that weren't replicated in other regions until much later periods. Ancient Chinese metallurgy also included the production of specialized alloys for specific applications. Chinese bronze mirrors contained alloy compositions that remained bright and reflective for centuries, using metallurgical knowledge that prevented tarnishing and corrosion. Some Chinese bronze formulations achieved properties that modern alloy design principles can explain, but that required extensive empirical experimentation to develop originally. The Greek fire used by the Byzantine Empire represents a lost military technology that combined chemistry and engineering in ways that modern researchers have struggled to replicate exactly. Historical accounts describe an incendiary compound that could burn on water, stick to targets, and continue burning despite attempts to extinguish it with traditional methods. Various theories about the composition of Greek fire have been proposed, but none have fully recreated the capabilities described in historical sources. Ancient glass-making techniques achieved optical and artistic effects that modern glass artisans find challenging to duplicate. The dichroic properties of the Lycurgus cup, which changes colour depending on lighting conditions, result from gold and silver nanoparticles suspended within the glass matrix. The precision required to create these nanoparticles through ancient glass-making techniques suggests sophisticated understanding of temperature control and chemical processes. Some ancient construction techniques produce structural capabilities that modern engineering is only beginning to understand. The earthquake resistance of certain ancient masonry structures results from design principles that anticipate modern seismic engineering concepts. The precise fitting of massive stones without mortar creates flexible structures that can move during earthquakes without losing their integrity. Traditional fermentation technologies developed by ancient cultures achieved results that modern biotechnology is working to understand and improve. Ancient fermentation processes produced specific chemical compounds for pharmaceutical, industrial, and culinary applications through controlled biological processes that selected for particular microorganisms and metabolic pathways. The preservation techniques used in ancient mummification processes achieved results that modern preservation science struggles to match. Egyptian mummification created preservation conditions that maintained organic tissues for thousands of years, using chemical treatments and environmental controls that demonstrate sophisticated understanding of biological decay processes and preservation chemistry. Ancient agricultural techniques sometimes achieved crop yields and soil sustainability that modern agriculture is trying to recreate through sustainable farming methods. Traditional agricultural systems maintained soil fertility across centuries without external inputs, using crop rotation, companion planting, and biological pest control methods that integrated ecological principles. These modern rediscoveries suggest that ancient technological development followed different pathways than our current approaches, sometimes achieving superior results through methods that we abandoned in favor of industrial processes that prioritized mass production over long-term performance. The gradual rediscovery of ancient techniques indicates that technological progress isn't necessarily cumulative, and that valuable knowledge can be lost and must sometimes be rediscovered through different approaches. The most profound technological achievement might be the one that leaves no trace at all. While we search ancient ruins for evidence of gears and circuits, for metals and machines, we might be overlooking civilizations that discovered something we're only beginning to understand. That true advancement lies not in conquering nature, but in learning to work so seamlessly within it that technology and environment become indistinguishable. Consider the possibility that ancient peoples developed what we might call ecological technology, systems that harnessed natural processes without disrupting them. Instead of burning fossil fuels, they might have learned to capture and direct energy flows that already existed in their environment. Instead of manufacturing materials that resist decomposition, they might have developed biological processes that created exactly what they needed, when they needed it, using resources that returned harmlessly to natural cycles when their purpose was fulfilled. Such technologies would be nearly invisible to archaeological investigation. A civilization that mastered photosynthesis enhancement might have created food systems that appeared to be natural forests, but actually produced yields that sustained large populations. A culture that understood soil chemistry and microbiology at sophisticated levels might have created manufacturing processes that used biological systems to produce complex materials, leaving no industrial infrastructure behind when the processes were discontinued. The energy systems of such civilizations might have been based on principles that we're only beginning to explore today. Biological fuel cells that convert organic matter directly into electrical energy could have powered sophisticated devices without requiring mining, smelting, or industrial infrastructure. Acoustic energy systems might have captured and transmitted power using sound waves and resonance effects that left no permanent installations. Transportation technologies based on understanding natural energy flows could have achieved remarkable capabilities while leaving minimal traces. Systems that used magnetic fields, atmospheric currents, or hydrodynamic principles might have enabled efficient movement across land and water without requiring permanent infrastructure or vehicles that would survive in the archaeological record. Even information technologies might have been based on biological or natural systems that integrated seamlessly with environmental processes. Memory storage using biological systems could have preserved vast amounts of information in forms that appeared to be natural forests, coral reefs, or other living systems. Communication networks based on biological or acoustic principles might have enabled coordination across vast distances without leaving technological artifacts. The materials science of such civilizations might have focused on enhancing natural processes rather than creating entirely artificial substances. Instead of developing metals that resist corrosion, they might have learned to guide biological systems that produced materials with exactly the properties needed for specific applications. These biomaterials would decompose naturally when no longer needed, leaving no permanent waste or industrial residue. The architecture of sustainable advanced civilizations might have been based on growing rather than building structures. Systems that guided plant growth, coral development, or geological processes could have created sophisticated living spaces that provided all the functions of conventional buildings while appearing to be natural formations. Such structures would be self-maintaining, environmentally integrated, and would return to natural states when abandoned. The agricultural systems of such civilizations might have achieved remarkable productivity through ecological integration rather than environmental domination. Instead of clearing land for crops, they might have developed forest systems that produced food, materials, and energy while supporting natural biodiversity. Such agricultural systems would be indistinguishable from natural ecosystems to modern observers. The medicine practiced by sustainable advanced civilizations might have been based on understanding biological systems at levels that enabled precise intervention without artificial drugs or devices. Therapeutic systems based on biological enhancement, environmental modification, or energy manipulation might have achieved remarkable healing capabilities while leaving no trace of medical technology in the conventional sense. The social organization required to maintain such technologies would itself represent an advanced achievement. Coordinating complex ecological technologies across large populations would require sophisticated information systems, decision-making processes, and cultural institutions that could preserve technical knowledge across generations without centralized industrial infrastructure. Such civilizations might have understood that sustainability requires not just environmental harmony, but also social and cultural systems that could maintain sophisticated capabilities across indefinite time periods. They might have developed governance systems, educational methods, and cultural practices that prevented the accumulation of power, wealth, or knowledge in ways that could destabilize their ecological integration. The transition to ecological technology might have been driven by understanding that conventional industrial development inevitably leads to resource depletion, environmental degradation, and social instability. Advanced civilizations might have learned to redirect their technological development towards systems that enhanced, rather than depleted, natural capabilities. The success of such technological approaches would be measured not by material accumulation or energy consumption, but by the ability to maintain sophisticated capabilities across geological timescales without disrupting environmental systems. True technological advancement might be invisible precisely because it achieves maximum capability with minimum environmental impact. This perspective suggests that the absence of obvious ancient technologies might not indicate technological primitiveness, but rather technological sophistication so advanced that it achieved its goals through integration rather than domination. The silence in the archaeological record might reflect not the absence of ancient achievement, but the presence of wisdom that we're only beginning to understand. So here we find ourselves at the end of this long journey through possibility, having wandered together through the shadows of what might have been. We've examined megalithic stones that whisper of forgotten engineering, ancient metals that resist time's decay, and maps that show lands that shouldn't have been known. We've considered the weight of deep time and how it erases even the most ambitious human achievements, leaving only the faintest traces for future generations to puzzle over. The question we began with, whether advanced technology existed in the past, remains beautifully unanswered, and perhaps that's exactly as it should be. Because this isn't really a question that demands a definitive yes or no. It's an invitation to expand our sense of what's possible, to hold space for mystery without abandoning reason, to acknowledge that the story of human capability might be far more complex and surprising than our textbooks suggest. We've seen how the preservation problem makes ancient achievements vulnerable to complete erasure, how catastrophic events can reset civilizations repeatedly, and how our definitions of technology might be too narrow to recognize capabilities that took radically different forms. We've explored the possibility that truly advanced civilizations might have learned to work so harmoniously with natural systems that their technologies became invisible, indistinguishable from the environment itself. Throughout this exploration, we've tried to balance wonder with skepticism, possibility with evidence, imagination with scientific rigor. The absence of clear proof for ancient advanced technology doesn't diminish the validity of asking the question. Instead, it reminds us that the universe still holds more mysteries than answers, and that uncertainty can be a kind of gift if we learn to receive it gracefully. What emerges from this inquiry isn't certainty about the past, but humility about how much we don't know and might never know. The archaeological record is fragmentary, the geological record is incomplete, and the ocean floor holds secrets that may remain forever beyond our reach. In this vast landscape of unknowing, we can choose to see limitation, or we can choose to see wonder. We can focus on what's missing, or marvel at what's been preserved against impossible odds. The technologies we've imagined tonight, whether they existed or not, serve another purpose. They reflect our own deepest aspirations for what human ingenuity might achieve. When we wonder about ancient flying machines, we're really wondering about our own relationship with the sky. When we imagine lost civilizations that lived in harmony with their environment, we're exploring our own hopes for sustainable futures. Perhaps the most important insight from our journey is that technology isn't just about tools and machines. It's about the application of intelligence to solve problems and enhance life. Viewed this way, a prehistoric person who could track an animal across varied terrain, predict weather patterns, and navigate by the stars was demonstrating technological sophistication that deserves our respect and wonder, even if it didn't leave behind circuit boards or concrete structures. The persistence of these questions across human cultures suggests something fundamental about our nature. We are creatures who look backward to understand ourselves, who search for precedent and pattern, who need to know whether we're truly alone in our achievements, or part of a longer, deeper story of intelligence flowering repeatedly across time. As you prepare for sleep tonight, let your mind settle into this expanded sense of possibility. The past may hold more surprises than we imagine. The technologies we consider so modern and unprecedented might have antecedents that we simply haven't recognized or haven't found. The silence in the archaeological record might be hiding achievements that would astound us, or it might be genuinely empty. But either way, it invites us to approach history with wonder rather than certainty. Sleep offers its own form of time travel, carrying us into states of consciousness that are both deeply personal and mysteriously universal. As you drift into that threshold between waking and sleeping, you're entering a realm that ancient peoples knew as well as we do, a space where individual awareness dissolves into something larger and more mysterious. And in that dissolving, maybe the questions we've explored tonight matter less than the spirit in which we've explored them. The willingness to wonder, to imagine, to hold multiple possibilities simultaneously without needing to collapse them into single answers. This capacity for sustained wonder might be the most advanced technology any civilization could develop, the ability to remain curious and open in the face of mystery. The ancient peoples we've imagined tonight, if they existed, would have looked up at the same stars we see, wondered about their place in the vast scheme of things, and felt the same mixture of insignificance and wonder that touches us when we contemplate deep time. They would have known the same rhythm of days and nights, the same cycle of sleeping and waking, the same drift toward unconsciousness that you're experiencing now. So rest peacefully, knowing that wonder needs no justification and mystery requires no solution. The questions we've shared tonight will wait patiently in the realm of possibility, ready to be revisited whenever curiosity calls. Whether ancient technologies existed or not, the capacity to imagine them, to wonder about them, and to explore their possibilities together is itself a kind of advanced technology, a meeting of minds across time and space that connects us to the deepest currents of human consciousness. Sweet dreams, fellow traveller in the landscape of wonder. The past keeps its secrets, the present offers its mysteries, and sleep provides its own gentle journey into the unknown.